Hello again. Now this is the last of the three video lessons to revisit the skills needed for success in our unit on the physical behaviors of matter. Here we go. Question 15 says the table below shows data for temperature, pressure, and volume of 4 gas samples. So we've got temperature, pressure, volume. Question reads, which two gas samples have the same total number of molecules? Now, if you recall from previous questions, we talked about Avogadro's hypothesis, which stated if we have the same conditions of temperature, pressure, and volume of any gas, the number of molecules will be the same. Take a look at this diagram once again, and it is showing you exactly that. For argon, oxygen, and nitrogen, different substances that even have different masses. Same volume, same pressure, same temperature, same quantity of substance, same number of moles. So, let's look for one that satisfies these conditions. Same temperature. We've got 100s and 200s. Let's look along this line. Temperature 100, pressure 2. Temperature 100, pressure 2. Volume 400, volume 400. Looks good. What about this? Temperature 200, temperature 200, pressure 2, pressure 4. That just destroys it right then and there. We are looking for choice A, and C will be the same. That brings us to choice 2. Alright, 16. Which Kelvin temperature is equal to 56 degrees Celsius? Well, previous questions did rely on this knowledge, and let me bring you back to the formula necessary, and it's right here. Kelvin temperature is equal to the degree Celsius plus 273. Let's get this out of the way, do the math. So we have the Kelvin temperature is equal to the degrees Celsius, 56 degrees Celsius, plus 273. What is that? 273 plus 56, 9. Okay, 7 and 5 is 12. 329. And there it is. Question 17. A gas occupies a volume of 444 milliliters at 273 Kelvin and 79.0 kilopascal. What is the final Kelvin temperature when the volume of the gas is changed to 1,880 milliliters and the pressure is changed to 38.7 kilopascal? Now, what formula should we use? We're looking here at our gas laws, right here. Gas laws. P1V1 over T1 equals P2V2 over T2, where P is pressure, V is volume, and T is temperature. Let's try to apply that. Get this out of the way. And remind ourselves of the formula. P1V1 over T1 is equal to P2V2 over T2. Now, can we find these variables? Once again, it says a gas. A gas occupies a volume of 444 milliliters at 273 Kelvin and 79.0 kilopascal. So my P1 is 79.0 kilopascal. My V1 is 444 milliliters. And my T1 is 273 Kelvin. My P2 is right here, 38.7 kilopascal. My V1 is 1,880 milliliters. And my T2, ooh, that was supposed to be V2. My T2, well, that is my unknown. Make that a question mark. All right. So this equation now looks 79.0 kilopascal times, let me make that a big dot, times 444 milliliters over 273 Kelvin is equal to 38.7 kilopascal times 1,880 milliliters over T2. Cross multiply and divide. Where this will bring you is T2 is equal to 566.267 Kelvin. Now the numbers did extend longer, but let's investigate the choices given to us. With the choices given to us, the only option that makes sense is choice 3. Now moving on to 18. How much energy is required to vaporize vapor? I have to think of a gas here, don't I? Vaporize 10 grams of water at its boiling point. Alright, so we're talking about energy. We must consider these formulas here. The heat formulas, Q equals mc delta T, Q equals mHF, that's for heat of fusion. Q is equal to mHV, heat of vaporization. Vaporization. I'm thinking gas here. Alright, so we have our formula. Q is equal to mHV. Now the question is, what is the value for HV? Let's take a look. The value for HV is identified right here on table B of the reference table, and it is 2260 joules per gram. Let's get this out of the way and apply the math. Once again, Q is equal to mHV, where we know what the mass is and we know what HV is. So it becomes Q is equal to 10.00 grams times 2260, and that was joules per gram. Multiply these together. Multiplying by 10 always adds an extra 0. Q is equal to 22600. What happens to the units? Grams are divided by grams. Our final unit is joules. Let's inspect the choices. Uh-oh, problem. It all says kilojoules. So we must convert joules into kilojoules. And if you recall, we have a line here that helps us with that. That's kids have dirty, and we said mouths, lips, and gums for the other units of the metric system. Drinking chocolate milk. In this case, we are moving from, let me choose a different pen color. We will be moving from a base unit of joules to kilo. Move the decimal 3 spaces. 1, 2, 3. Do we have a match for a choice for an answer? Do we have 22.6 up here? And we do. Question 19. The graph below represents the relationship between temperature and time as heat is added uniformly to a substance, starting when the substance is a solid below its melting point. It's a solid below its melting point. The question, which portion of a graph represent time when heat is absorbed. Heat is being added through time. When heat is absorbed and potential energy increases while kinetic energy remains constant. Now we must recall, we did say that temperature actually means average kinetic energy. So we are looking for a time where this value does not go up. The only places for that are right here and right here. So if kinetic energy is not changing, potential energy must be changing. We are looking for a choice that has B and D, and there it is. And finally, this is a little bit of a tricky question because all of our experiences with those heat formulas has been related to water. Pay attention to the subtle details given here. What is the total number of joules of heat that must be absorbed to change the temperature of 100 grams of ethyl alcohol from 25 degrees Celsius to 30 degrees Celsius? With this question, they're giving you the specific heat capacity of ethyl alcohol. And instead of it being water at 4.8, let me show you that. Remember, for water, the specific heat capacity for water, let me grab the right pen, for water, the specific heat capacity was 4.8 joules per gram Kelvin. Well, you're not dealing with water this time. You're dealing with ethyl alcohol. And because of that, they gave you the values, 2.60 joules per gram degrees Kelvin. Now, the other thing that must be considered is which formula am I going to use? And with our heat formulas, we have Q is equal to mc delta T. Q is equal to MHF, heat of fusion. We're not dealing with a phase change here, so we can't use that one. Or Q is equal to MHV. Again, a phase change would be involved here. Plus, we notice that there is a temperature change in the question. We must be using MC delta T. And let's remind ourselves of that, or writing it here. Q is equal to MC delta T. Now, what are these values? Q is equal to the mass. There it is, 100 grams. Let's put the decimal point in there too. In the event that they asked for specific, significant digits, that would be important. Now, what is C? There it is, 2.460 joules per gram Kelvin. Now, what is that temperature change? Well, it's a 5-degree temperature change in the Kelvin, the Celsius scale, which also matches a 5-degree change in the Kelvin scale. So we put a 5K there. If we wanted to address the units first, grams divided by grams, they would cancel out. Kelvin divided by Kelvin would cancel out, and we end up with Q is equal to 246. Let me backtrack. Let me just do all that math together. Q would equal 1,230 because you would multiply all three together, joules, and there it is. I hope this video helped. Have a good vacation.